Hi everyone, here we are again. We are looking now at section 5.3 in chapter 5 about discrete probability distributions. In this case we're looking back again at the binomial distribution, but specifically we're looking for things about the mean and the standard deviation of the binomial distribution. Okay, that's what we're looking for primarily. So in the last section, 5.2, we looked at probability. We found the nice probability formula, and we looked at how to use StatCrunch to evaluate probability for binomial distributions. Okay, now it turns out that if you have a binomial distribution, you can shortcut that long table method we used in section 5.1. If you recall that table method, we had to make the probabilities of each x times its probability and then add them all up. And if we wanted the standard deviation, we had to do something similar, adding the x squared column and the x squared times the p of x's, and it was pretty messy. But we are so lucky because if it's binomial, then there are shortcuts. And for a binomial distribution, the mean of the x values is equal to just n times p, right there. And the standard deviation is this square root of n times p times 1 minus p. Okay, the n times p formula makes a lot of sense, because if the probability that something is successful is, say, 20% of the time it happens, and if n happened to be 100, then the mean is what you expect, which would be 100 times 20%, which would be equal to 20. So 100 times 0.2 is equal to 20. That's what you'd expect. It's 20%. The standard deviation, there's not really a good way to interpret that where you would say, wow, that makes sense, it's obvious. But with the mean, there is. Okay, so for example, if we wanted to find the probability about Steph Curry making free throws, those of you that are basketball fans probably realize that Steph Curry is a very good free throw shooter. He makes about 91% of his free throw attempts in general. And so in this case we have he's going to take 20 free throws in a playoff series, and x is the number of free throws that he makes. Now this is a binomial experiment because he's taking 20 free throws. That's the fixed number of trials. The probability is 91%, is the same for all of his free throws. His free throws are independent of each other, and of course there's two outcomes. He either makes his free throw or he misses his free throw. So there you have it. Okay, so in this case, since n equals 20, he makes 20 attempts, p is 0.91, it's going to be a binomial distribution, and we have to express this p, even though it was given as 91%, we have to write it as 0.91 in decimal form. Alright, so what's the mean that we'd expect? Well, the mean is the n value, which is what I've written in blue right here, n is 20, and p is the probability that he makes any one single shot, that's 91%, or 0.91. When you multiply them together, you get 18.2, which means that we expect him to make about 18, probably. If he takes 20 free throws, he's probably going to make around 18. He might make 19, he might make 17, he might make all 20, but it's somewhere around 18. The standard deviation is a little more complicated. The formula is you plug in the n, which is the blue, the red is for the p. So we plug it 20 times 0.91 times 1 minus 0.91. Now remember, with order of operations, you do what's inside these parentheses first. So 1 minus 0.91 is 0.09. We then would multiply these three numbers together to get 1.638. And then we square root that and we get 1.28, or about 1.3. So the way we interpret these numbers is we expect that Steph Curry is going to make about 18.2 free throws on average for every 20 attempts that he makes. And the standard deviation is going to be about 1.3. So plus or minus, 1.3 is probably about what he's going to usually get. So generally 17, 18, 19 out of 20 attempts. Okay, now you could make a table. I made a note here. If you want to make a table for all 20 outcomes, it's possible. And if you went through and you did the x times the p of x's and added them all up, you'd get the same thing. Okay, the second topic in section 5.3 is when we're describing distributions. There's always three things that we talk about when we describe a distribution. We always talk about the center, and we're going to be using the mean to describe the center in general. We want to talk about how widely it's dispersed, or how widely it's spread out. That's the standard deviation. And we talk about whether or not it's bell-shaped, which is the shape. So you got the center, the dispersion, and the shape. Those three things. the center, the dispersion, and the shape. Whenever we describe a distribution, those are the three things that we must include. So you might be asking yourself, but wait, if it's skewed, I thought we were supposed to use the median and the mean and the IQR to describe the center and the dispersion. And that's true. So we really want to be able to know, all right, well, the mean and the standard deviation are going to be very helpful, but mostly in situations when we have something that's bell-shaped. So when is a binomial distribution going to be approximately bell-shaped? And that's in this blue box right here. Years ago, people figured out that if you have large enough sample sizes and the probabilities, the p and the 1 minus p, are not too extreme, if you plug them into this formula and you get more than 10, greater than or equal to 10, then it's going to be pretty close to bell-shaped. It's not perfect, but it's going to be pretty close. Okay, so that's the idea. It's not perfect, but it's going to be close if the n times the p times 1 minus p is greater than or equal to 10. By the way, this n times p times 1 minus p is also known as the variance. We don't really use that in anything, but eventually, if you took more statistics classes, you would study this thing called analysis of variance, and it would be very important in that class. Okay, so let's look at this situation of Steph Curry taking 20 free throws, and let's find out if this histogram, if we look at it for the binomial probability distribution, if that's going to be bell-shaped. All right, we know n was 20, and the probability he makes a shot was 0.91. If we plug them into the formula, n times p times 1 minus p, that would be 20 times 0.91 times 1 minus 0.91, and then we multiplied that out. We actually did that a few minutes ago. We got 1.638. Okay, now that is not bigger than 10, so this distribution will likely not look very bell-shaped. It's probably going to be pretty skewed. So if we used Excel, we can create a histogram that's pretty likely skewed to the left, and this is the one that I made. This is the probability for the free throws that he makes, and you can see it's definitely skewed off to the left here. So it's not very bell-shaped. And the fact that this was not 10 means that it's not going to be likely bell-shaped, and it's not. All right, so the last example then is what happens where something is. Let's say, hypothetically, a student forgot to study for a 100-point question multiple choice test. And each question has 4 possible answers, A, B, C, or D. So the student has decided they're just going to guess, and they're just going to fill it out randomly, and they're not going to even try to read the problems. They're just going to make a bunch of guesses and see what happens. So let's let x equal the number of answers that he guesses correctly. So A is, why is this a binomial discrete random variable? What makes this binomial? So going back to 5.2, there's 100 questions, which is the fixed number of trials. They are independent because if you get the first question right or wrong and you're guessing, it doesn't affect whether you get the second or the third or 38th or 19th or whatever. They're independent. There's 2 outcomes. You either get it right or you get it wrong. 2 outcomes is it. That's the bi part of the word binomial. It's 2. The probability of getting a question right is just going to be 1 out of 4 chances for every single problem. And so in that case, it's constant and it's always the same. Okay, so let's find the mean and the standard deviation for the number of correct guesses that you would get. So if n is 100 and p is 0.25, that's 1/4. That's 1 out of the 4 answers, A, B, C, or D. Then the mean is going to be 100 times 0.25, which is 25. So we expect you're going to get about 25, 1/4 of the problems right if you're just randomly guessing. The standard deviation for the number of guesses that you get right is going to be equal to np1 minus p. You do the 1 minus p first, make that 1 minus 0.25 is 0.75. Multiply these numbers together and you get 18.75. And the last thing you do is you square root it and you get about 4.3. So the interpretation is we expect students who are guessing to average 25 correct responses with a standard deviation of 4.3 correct responses. So probably somewhere between 20 and 28, 29 is about what you'd expect to see out of 100 for somebody who is just guessing. All right, so now if we look at the binomial histogram, is it bell-shaped? Well, if you're looking, you can see, yeah, that looks pretty bell-shaped. Can we check that condition? Sure. Is the np1 minus p greater than or equal to 10? Yeah, because if you multiply it out, and we just did, it was part of our standard deviation formula. We had 100 times 0.25 times 1 minus 0.25, and that was 18.75. It's bigger than 10, so it's going to be bell-shaped. All right, and that's it. So I got this nice here, nice picture here. And so guessing on a 100-point question, multiple choice test, this is going to look pretty bell-shaped. So lastly, would it be unusual if the student guessed 40 or more questions correctly? Well, if you look at the picture, 40 or more, 40 is way over here at the tail. You can see these are even already marked a little bit red. It looks pretty unlikely you're going to be scoring up here. And so again, if we just go back to StatCrunch, which I did, the probability that x is greater than or equal to 40 is about 0.0007. So it's really, really, really unlikely that you would score a 40 or a 50 or even get, to get a C. There's very little chance if you're just guessing. Okay, well that's the end of the video lesson for section 5.3. I hope it's working for you. Let me know and I will talk to you soon. Okay, thanks. Bye.